This is NEAF Talks.
And now, ladies and gentlemen, the hardest working MC in the cosmos, Vincent Coulihan.
Hey, thank you. Thank you very much. Thanks. Hey, a big thank you to the great audience and crowd here today at NEAF. And it really is a great pleasure to be introducing our keynote speaker today. It truly is going to be a fabulous experience for all of us. Our keynote speaker became an astronaut in 1996. He has a PhD from the University of Arizona in space physics. He served on the following missions. On Expedition 6 in 2003, he was a science officer. He operated a robotic arm on STS-126 in 2008. He was the flight engineer for Expedition 30-31 in 2012, where he lived on the space station for more than 6 months. It is with great pleasure that we introduce to you at NEAF 2019, Dr. Don Pettit. Thanks, Don. Thank you.
I love the concept of a frontier. Frontiers are places where our normal intuition doesn't necessarily apply. Frontiers are places where the answers aren't in the back of the book, and you might have to figure something out for yourself. Now, frontiers are all around us. They could be in the bottom of the ocean, under the stage of a microscope. For a lot of folks here, it's through the eyepiece of a telescope. My frontier is space, and that's a picture of my home. But really, I like to refer to this as my observatory. And you do have to make sure that when you have this kind of observatory, you don't have a roll-off roof. Now, this is a window on space station looking out. We are somewhere over China, looking past the Himalayas to India. And if you know where to look, you can see Mount Everest. It's that mountain that's sticking way up there. Yeah, you can all see that. But Mount Everest is in this picture. And I like to use this to illustrate a concept of the frontier. You could go to station as a new astronaut, and you could think, dozens of people have looked through this window before me, and they've taken tens of thousands of pictures. And so why should I bother to do anything? Because it's already been done. But what you need to realize is you're in a frontier, and you can make new observations just because you've got a different kind of brain than anybody else that's ever been there. And so this is window on station. I'm going to change the settings on the camera a bit. And look, whoa, what's that? It's the same window, the same planet, the same view, but I've tweaked it up for night photography, and you can see aurora. But wait, there's more. Change it again. That's a 30-minute stack time exposure. And you're seeing all kinds of really neat phenomena there. And I like to show that just because somebody else has done something before you doesn't mean that you shouldn't try it and see if you can make a different observation. So when you are in a frontier, the very concept of been there, done that, does not apply. So this gets me to the subject of my talk. I like to call it Science of Opportunity. And this is on the International Space Station. And we have programmatic science. And it's well planned, well thought out. It flies up from the ground, and we're like glorified graduate students, and we do this. But because we do have a brain, and because we do have off-duty time, you can't work 24 hours a day for 6 months at a row, you can think about things that maybe folks on the ground hadn't thought about, and you can do science of opportunity. And this happens in our research laboratories here on Earth, where it's a Saturday night, the major professor's gone, the graduate students have been turned loose in the lab, and they come up with some new ideas, and oftentimes those ideas turn into seeds for future programmatic research. And so on Space Station, it's no different. So what I'm going to talk about is a number of vignettes dealing with some of the opportunistic science that I did on station. So I thought, instead of giving it that boring title, let's call it Techno-Stories from Space. But then I thought, you know, let me see if I can come up with a better title. So here is a title I really like. Scientific Advances from What Appears to be Goofing Around in Space. So let's goof around a little bit. Okay, this is a big sphere of water. It's the size of my head. And it's held in place in front of the video camera with that little skip of wire. And on the side, I've got a syringe, and I did a little timing, and I can put a 25 cc puff of air on this sphere in about 100 milliseconds. And the only reason I made this sphere was I knew the ratio of surface tension force to inertial force was going to decrease as the sphere got larger and larger and larger. But what exactly was going to happen, I hadn't a clue. So let's go ahead and do the experiment. Puff. It's like, whoa, what is happening there? It looks like some hapless planet that gets whacked by an asteroid, right? And it's so cool, we're going to see it again. And this is real time. Look at that, an impact crater. There's ejection of material. This is like throwing a rock in a spherical pond. And the ripples, instead of going out into a plane, are forced by boundary conditions to stay on the outside of a sphere. Oh, and this is in slow motion. We're going to see it a time or two. Oh, look at that, slow motion, impact crater, spurt, ripples on the outside. They diverge to the diameter chord. They converge at the antipoid. That's 180 degrees from impact. A spurt goes out. It collapses back down. And you get this delightful interplay of surface waves until viscous dissipation dampens the whole thing out. And I had no idea what was going to happen before I did this. All I knew was, something was going to happen. Let me give it a try. And, my jaw dropped down. Look at that. I've never seen anything like that. But after I saw this, I was able to use my existing body of knowledge to explain what was going on. Okay. So after I did all of this, I was at a physics of fluids conference, and I gave a paper on this, and then the video was shown, and the physicists, the fluid physics people there, voted this video the #1 video of fluid physics for 2005. And I was just goofing around. Okay, I'm going to roll a little video here. It's got an audio track. Let's see how that works.
Take one.
I'm Don Pettit. I'm on the International Space Station. I have a Lego kit here, and we have the official NASA Space Station Lego instruction booklet. The whole concept of Legos to me is not following the instructions. So I'm going to just give the instruction booklet a push. Look what I made. Got a big rubber band here. Then I used some Lego wheels. This is the basis for a Van de Graaff generator. Instead of having a spherical collector, let's make a cylindrical collector. I happen to have some aluminum foil, and so I rolled it into this cylinder. This may not be ideal. It's probably going to be good enough. I happen to have a drill driver here. So this isn't little kid stuff anymore. I found a sphere. I can get sparks here about 2 inches long. That's probably close to 120,000 volts. So I was just playing with Legos, right? Well, look at this. Now here's drops of water. They get charged, and you squirt them out around this charged sphere, and they go into orbit. It's not a gravitational orbit, but it's a static electric orbit. So the ratio between static electric force and gravitational force, static force loses. But now you're in a weightless environment, and look at this. I started to squirt everything I could find on the sphere. And that's water, and I put every other kind of thing I could find, coffee, tea, milk, and it makes these delightful cones. And this is a ratio of forces, surface tension force and charge force without significant gravitational force. And so I played around with this a bunch. And then I gave a talk at this fellow from some obscure place. It's a New Jersey Institute of Technology. He came up to me and he said, you know, I'm doing research on these things, these little pointy things. He says they're called Taylor cones. And these charged cones are fundamental for things like inkjet printers and any kind of static electric droplet spray technique like some of the spray painting they're doing in industrial processes. And so we shared data, and we came up with this. So this is a plot of a scaled time along the x-axis and a scaled length distance along the vertical axis, and all his data points are there, and the largest Taylor cone he could make was 0.5 millimeter. And that's because gravitational forces dominate in this kind of regime. And then he had some graduate students, probably chained them to a desk computer in a room, maybe threw a hamburger in once a day, and they analyzed my video, and that's all the data up at the top. 5 centimeter long Taylor cone. So we extended the knowledge by 2 orders of magnitude. And then you look at the slope of the line going through, and the slope of that line also agrees with standard theory on this. So after doing all of this work, we published a paper in Phys Rev Letters. And this is a high-quality publication. And notice scientists tend to choose really dynamic names for things like detection of a dynamic cone-shaped meniscus on the surface of fluids in an electric field. You can't even say it with one breath. Now, what's really good is buried in this paper, in Phys Review Letters, is this part. Van de Graaff generator assembled from Legos. Phys Rev Letters. And we were just goofing around. Okay. How many people grew up reading this? Okay. Now, I need to point out this was written in 1953, so that kind of dates some of the people here. But I really like this book, Tintin Explores the Moon. And it has some amazing clairvoyance in there, written before we even had launched an object into space. And notice the rocket looks a lot like a V2 rocket. But here they say, moon rocket to Earth. This is Professor Calculus. Even then they realized you needed math and science to get places, right? So if you want to explore space, if you want to do what I do, you got to know your math, okay? And then one of the crew members, this guy's Haddock, and since it's a space ship, they figured, well, a ship is a ship, so we need a sailor along. So there's Haddock going to the moon, and he figured, I'd better learn a little astronomy, so he brings his astronomy book. And then, of course, he opens it up. And I need a book like this on my next mission. Maybe I could get one of the authors here that write amateur astronomy books. Maybe we can figure out how to make a book like that. But the neat thing is, in 1953, they realized that a standard glass is not going to work in a weightless environment. A drinking glass, a coffee cup, a snifter, whatever. These things are gravity machines. And so he's chasing his whiskey all around the room, and so's the little doggy. And then, of course, you end up with a big mess. So, fast forward to the space station. Since cups don't work, the NASA engineers have come up with a perfectly fine solution. It's called the drink bag. And it's just like the juice bag you get from the grocery store. And you can put all kinds of things in it. You can put freeze-dried coffee in that. And so here I am with our galley behind my showing where you can inject the water into your bag of coffee. Okay, and so we drink all our fluids through a straw from a bag. And I thought that's a little bit on the space gauche side. And I wanted to have a real cup, an open container. And then I was on orbit, and I got this flash from my surface chemistry classes that I took in school. And I was probably sitting in the back of the room looking like I was sleeping, at least from my professor's point of view. And unbeknownst to him, I was subliminally learning something. And I remembered some really neat equations from surface chemistry. And so in a flash on station, I took a piece of plastic and some tape, and I taped up this cup. And it's got a special structure to it. It has an acute angle that runs up the side. Now, I got the plastic from our emergency procedures. I figured they wouldn't miss just one page from the emergency procedures. So let's see how this cup works. So there it is. I'm putting some tea in it. And notice the surface tension drives channel flow up that acute angle, and it parks itself right next to the lip. And if that angle is less than 2 times the quantity, 90 minus a wetting angle, you get this channel flow. And there's Steve Bowen and I, and we are drinking from an open container and having a toast for the first time in history of spaceflight. And see, and you could drink these things to dryness. And now for the first time as a crew, I made 6 of these. We could have a toast, a proper toast with tea and coffee in a manner commensurate with how everybody here does things on Earth. And just think, you come in from doing a spacewalk, using the spacesuits from the fellow that talked about it, and maybe you flew the robotic arm and you captured the first commercial vehicle coming up the station. And, you know, no pressure, no pressure. The future commercial space just rests on your ability to run this thing that's like a fancy backhoe. And so after a hard day's work like that, you can have a communion with your crew in a manner commensurate with how life is on Earth. Yeah. So, what do we have now? We've got the second generation. These are 3D printed out of food-grade plastic. And we have these on station. And this shape was designed with a colleague of mine, Mark Weislogel, from Portland State University, and some of his graduate students. And the shape of this cup is strictly defined from the fluid physics The mathematics of fluid physics in a weightless environment. There's no art in this at all. Strictly math and fluid physics. And after we got this, we wrote a proposal. And actually, Mark Weisslager wrote the proposal and got it submitted to NASA. We got funding. And so this became a formal experiment on space station. It was called the capillary beverage experiment. And we flew these cups, and we shot videos, and from these videos, we could look at flow fields, and we could get data from this, real data. Again, from graduate students chained to a desk, 2 hamburgers a day, and you get your data. And so now you can get position as a function of time, get velocity, you can get acceleration, you can get frequency, you get all of the scientific data, and now you can take all of this and you can write up papers and publish them because that's what scientists do. Now, we still had coffee cups on station, and so what do you do with a coffee cup? You drink coffee from it. And this is Samantha Cristoforetti, an Italian astronaut, ESA astronaut, European Space Agency. And she was up there, and she talked ESA into making an espresso machine. And I'm talking real espresso. And they did such a good job, went through all of NASA's safety reviews and everything, that flew up the station. And so she was the first one to have a real cup of brewed coffee in space, and she was drinking it in a room with a view from one of these space cups. Now, but there's more. When this picture came down, I looked at it, and I looked at the espresso in the cup, and I thought, something isn't quite right there. Let me take a peek at it. And so here's an enlargement from that picture. And look at that. The bubbles from the crema, instead of floating on the top, which you don't expect them to, you expect them to be uniformly mixed throughout the volume, but they spontaneously formed structure. It's like, whoa. And then here's Earth espresso in conjunction with space espresso. And if you look at this with a high enough resolution, the structure that's formed almost looks like little galaxies and things from a Hubble Space Telescope picture. And it's like, what is going on here? And Mark Weisslager and I are still pounding our heads on the chalkboard because we can't figure out exactly why you get this spontaneous structure forming from this random situation of bubbles floating in your espresso. And this is an example of a different kind of discovery, because you can make a discovery that you have no idea what's going to happen. You make the observation, and then you see what happened, and then you use your existing models and theory and math, and then you explain what just happened. And then sometimes you make a discovery, and it's like, oh, I don't know what's happening. And that's when you know you've really advanced things. So here we are now with 3 generations of space cups. There's the original one that I made on orbit, and then we have the plastic 3D printed ones, and then we've got slip cast porcelain ones. And those are mostly for demonstration down here because you don't want to take something that breaks and makes little shards floating around. But as a result of all of this goofing around, we got a patent. And this is the first patent granted for something invented in space. Everything else is invented on Earth, built on Earth, and flown in space for use. But this, I was floating in the U.S. lab, and I made this in Node 2, and this is, invented in space, brought to fruition in space for use in space. Well, we got a second patent on the advanced design. And then we started publishing papers. This is Journal of Fluid Mechanics. And again, really cool titles, right? Quasi-steady capillary-driven flow in slender containers with interior edges. right? That lets you know it's a space cup, right? And then this is a proceedings from a APS meeting on fluid physics and drinking in space, a capillary beverage experiment. And we're in the process of writing up all that data and everything we learned with the second generation cup. And then NASA and Space Center in Houston decided to have a space art show. And I was asked to put a couple cups in. So there I am, proudly showing off the cups, all the different generations. And because of this, we were asked to send a couple cups to some obscure place in London. It was called the Beazley Museum of Design. And unbeknownst to us, their staff and patrons choose a design every year that is the design of the year. And the Space Cup was chosen, the Beazley Museum Design of the Year for 2016. And, you know, we were just goofing around, right? We just wanted to drink some coffee. Well, then there's this other obscure museum, some museum of modern art. It's I forget where it is and what it's called, but it's MoMA. Has anybody here ever heard of MoMA? There's now a set of these cups in the archives at MoMA. Okay, so let me shift gears a little bit. This is goofing around inside a station. I'm going to show a few things dealing with amateur astronomy kinds of goofings around. And so this is a series, a NOVA series that was shown on PBS, and they called it Naked Science. And good thing it's not about naked scientists. That would be pretty bad. But it's Naked Science. Okay, and they had one program that was on a planet formation centered around Earth. And I'm going to play just a short section from that.
Until recently, what turned this dust into a planet was a mystery. Then, in March 2003, a lighthearted experiment on board the International Space Station led to a significant discovery.
Don likes to mess with things, and one of the things he messed with was putting things in plastic bags, granular solids like sugar, salt, instant coffee. He put them in a bag, inflated the bag, and shook them up just to see what would happen. And what happened was the little particles formed up into clumps like dust bunnies instantly.
When he saw a video of the experiment, Love realized that he was witnessing a significant discovery.
And Don shot this video down. He said, "This is cool, isn't this neat?" And showed all his little videos and his different substances and the different bags. And I said, "Don, yeah, that is neat. Actually, you've solved a very old problem in planet formation."
In zero gravity, the crystals behaved completely differently to the way they behave on Earth. In the first few seconds of its life, our Earth may have looked something like this.
So on subsequent flights, I kept flying more stuff to put in plastic bags, and I actually got a hold of some chondrite, crushed chondrite meteorite material and chondrules. And then we flew some test particles that were dielectric and some that were electrically conducting, and conducted a whole series of experiments with this, or demonstrations on station. And here's one. This is just one of the little plastic bags with some sugar in it, and watch what happens. So there it is. You shake it up, and you got all these sugar particles. They're 0.5 millimeter to 1 millimeter in diameter. And as a function of time, they come together, they clump, and then look at this. After a while bouncing around each other, they compact each other, and you end up with asteroids inside of this plastic bag. And so in planetary formation, Stan Love was the fellow that was being interviewed. He's an astronaut. Before he became an astronaut, he was a planetary scientist. and he was studying planetary formation. And he happened to be at Mission Control doing Capcomming when I downlinked the initial video. And we started talking like scientists really talk over space to ground, which is unusual because usually space to ground is pretty terse. It's like two fighter pilots talking to each other. And we were talking like scientists, astronauts. And Stad said that this could help show planetary formation, and I commented, we're going to need a bigger bag. So what happened with all of this? Well, we published a paper. And this is in LPSC, the Lunar Planetary Institute's annual planetary meeting. And then, so we published that. And then we published another paper, and this was actually in the Journal of Planetary Science, and particle aggregation in microgravity, informal experiments on the International Space Station. I wanted to put goofing around, but Stan didn't think that was that sounded too well. And then, partly as a result of all of this, and partly from other things, I ended up getting an asteroid named after me. And again, you know, it's just goofing around with stuff in a bag. Okay, polar mesospheric clouds, also known as noctilucent clouds. These are thades, these are clouds that form at about 82 kilometers. They're on the edge of space. They're thin. This layer is only about 2 kilometers thick. And they're thin, they're gossamer, they're hard to see from Earth. You can only see them when you have a dark background, but they're illuminated by the sun. And you can see them really well in orbit. And I started to photograph these things. And you know, you could take just a bunch of happy snaps and kind of forget about it. Or you could take happy snaps and then write down information in your notebook like good scientists do. And you can talk about field of view, and you can talk about other things going on and make a complete observation. And you can routinely do this time and time again. And you can create instead of just a bunch of pretty pictures, you can create a data set. And because of this, it turned out there were some satellites that were also recording polar mesospheric clouds at the same time. And I ran across the people who run those satellites, and we were able to coordinate our data. And this was a poster session at AGU, which is an annual conference for planetary people in San Francisco. And we were able to make a paper out of the coordinated observations between space station, a space platform, and the satellites. So again, the way you make an observation, if you repeat an observation over and over, and even though that individual observation may by itself may not be significant, but if you do it over and over again and you record what's going on at the same time you're making that, now you have a data set. You're no longer goofing around. Or maybe you're still goofing around, but you can make something meaningful. Now, this is Montreal. And during my first mission, 2002 to 2003, 400 ISO was about the fastest digital cameras we had. And to take pictures of cities at night, incredibly beautiful things that most of the people in this room probably go the pox because that's our light pollution, but there's still interesting structures or human-born structures to look at. And this is about the best you could do because it's about a second, maybe second and a half exposure. And the focus is a little bit on the soft side. And so I wanted to do something better than that. So I cobbled this up from junk that I found on station. And the big black thing, that's a mount for the IMAX movie camera from a previous expedition, and we no longer had that on orbit, so it was just waiting to get burned up in the atmosphere. And then I put 2 cameras on there. One has a long telephoto lens that you can look through, and then the other camera has a shorter lens and a cable release, and you could take pictures with it. And then I have a screw that I could drive with that drill driver, and I got that long threaded bolt from one of our resupply cargo vehicles that ends up burning up in the atmosphere, and I figured they're not going to miss one bolt. So I built that bolt into this thing, and here's how it works. So you look through the camera with a telephoto lens, and you line up fades on Earth, and then you squeeze the trigger on the drill, and you adjust the rate till the cities are stationary, and then you snap a picture. And then you just keep doing this over and over again. And since we got a whole room full of amateur astronomers, this is nothing more than a barn door tracker. Except a barn door tracker, a simple hinge and a threaded bolt, and you move it with the camera on, and you could do a long time exposure on Earth to counteract Earth's rotation to take pictures of space. And here I was in space counteracting orbital motion to take pictures of Earth. And so there's the best picture that we were able to do of Montreal hand tracking. And here's what it looks like with this barn door tracker. And so once we got this technology developed, then what you do is you start taking pictures every time you have any off-duty time of all these places. Like, anybody recognize that? Chicago. How about this? And this is a mosaic. And you can start to take these overlapping pictures. You can make these mosaics. That goes from Los Angeles down to San Diego. And you can zoom into these shades kind of like Google Earth. And then this is New Orleans. And you can see that that bright spot, that's the French Quarter. And I think I took this about 2 in the morning. So it showed they were probably having an amateur astronomy conference going on there. And then this is Las Vegas. And to my eye, it may actually be the brightest spot on Earth. I haven't made any measurements to show whether that's true or not, but it certainly is the beacon of humanity. Now, time has advanced. We have much better cameras now, and we could get these kind of pictures, and crews are taking these pictures by the thousands all over Earth with our modern digital cameras, and you can do hand tracking. So that barn door tracker ended up going on one of those cargo vehicles that burns up in the atmosphere, and anyway, that was the end of that phase. But in the early part, we got a paper on this. And this is published, the main author is this guy by the name of Chris Elveridge. He works at NOAA out of Boulder, Colorado. And so we wrote this paper, and then we got another paper, and then we got another paper. And it's just goofing around. So the standard star trail pictures, we love to take these. You put your camera on a tripod, and you do a time exposure over multiple hours, typically stacking shorter pictures together, and you get this. This is in the San Francisco volcano region, north of Prescott, north of Flagstaff, Arizona. And we are now taking astronauts there for geology field training in preparation of going back to the moon. And there's lots of good things that you can learn there. Well, I'm just showing this picture as a reference, a ground reference, and being an amateur astronomer, I wanted to do the same thing from space. So there's a star trail picture from orbit. And this is about 30 minutes of stacked images, and just the phenomenology that you could see in this picture, I could talk about that alone for maybe a half hour, 45 minutes. Let's see. Nobody has anything to do after this, do you? I won't go into that, but there's a lot of neat detail. See, the cities are moving, streaking by because of orbital motion. That thing that looks kind of like a slice of key lime pie along the edge, that's our atmosphere. Scale height about 120 kilometers, and that's all we have. And then those little white dots, that's a single thunderstorm as a function of time, where it goes flash, and then there's orbital motion, and it goes flash. And so you have a time history of a thunderstorm. You could see stars moving, and as they get deeper and deeper in the atmosphere, refractive index gradients increase, and the slope of the curve of the motion of the star changes. That's not Polaris. That's the pitch axis of station. So it's the complement angle, 90 minus 51.6 degrees projected out into space. Let me go through a few of these. Here's another one. This one shows a single thunderstorm. This is another one that shows the bane, the pending LED bane to amateur astronomy. Cities are starting to have these pastel colors that you can't filter out with line filters anymore. Anyway, they're pretty from space, go figure. And then here's this picture. This is a cool picture. There's a lot on this. We're going over the ocean near the Falkland Islands, and those streaks in the water are oil platforms that are out there lit with xenon lights. And you see the atmosphere on edge. You see a little bit of sunrise coming up there. That triangular shadow on the module, that's the Japanese JAXA module. That triangular shadow, that's the shadow of the cupola where I was taking this picture. And see that little flash that's kind of going through the atmosphere? That's an iridium satellite flash. And an amateur astronomer colleague of mine, Rob Matson, he's in Los Angeles. He sent me an email on station, and yes, we can get email. And he said, if I modified my code for predicting iridium flashes, would you be interested in looking for them? And I sent him an email back. Well, of course I'll look for them. So and think about it, an iridium flash. It's a small angled beam of light that reflects off an iridium satellite, and it gets projected on Earth, and the spot size is maybe 2 or 3 kilometers in diameter. And if you're standing in that spot, you could see this flash in the sky for about a second that's brighter than Jupiter. And he's got an algorithm that'll predict that, and to modify that so it goes from one orbital platform to another, I thought, wow, this is going to be a neat exercise. He modified his code. He sent me the results, and I set up a camera, and I waited, and no flash. And so I sent him an email back. No, it didn't work. And then a couple days later, he sent me some more predictions. I set up cameras. No flash. So I sent him email. No flash. And we did this for weeks. And I got to the point where I wasn't even setting up a camera anymore. And after about 6 weeks, I was just looking, and there was flash. It's like, wow, you got lucky. And about 5 minutes later, he'd predicted another one. So I sat there. And it's pretty hard duty in your off-duty time to sit there and look out the window, And 5 minutes later, flash, another one. And then another one. And so he, in this iterative manner of working together as a team, we worked for weeks and weeks and weeks and finally got it to an end result. And so now, anytime you want to do an imagery of an iridium flash on station, Rob's the guy to get the algorithm to get that information, and that's the result of that. Now, since these star trail pictures are sequentially stacked, shorter images. You can make a movie out of them. And so here's a movie. And so you could see the cities coming at you. Look at that. There's a thunderstorm. And you can see the stars tracing trails. And they initially start out as point, and then they make their arcs. Really neat. And that's basically just goofing around. So this is my last slide. And frontiers are amazing places. Not everybody wants to go to a frontier, but they are places that draw a small fraction of humanity, and you can make observations and you can discover things that initially just enrich your mind and maybe tickle your imagination. But ultimately, these discoveries over a long period of time lead to a society that thrives. And I think a metric to how viable a society you live in can be seen by how much are you willing to invest in doing exploration in the frontier. And when you do go to the frontier, you're going to have a program. You're going to have some kind of programmatic effort that you need to follow, and it's been well planned and well thought out. But because you are there and you can, and maybe you could think about things that other people that didn't go to the frontier, you might be able to think about something that they couldn't think about because you are there. In your off-duty time, you can do opportunistic scientific investigations, and maybe there'll just be an educational demo for students. Maybe they could lead to something meaningful. Maybe you're just goofing off. Thank you.
Hi, I'm Dave Eicher, editor of Astronomy, and I'm here in beautiful, sunny California at Celestron, the world's leading manufacturer of telescopes. Today, we're going to get the lowdown on a secret, a new hot product that's unlike anything you've ever seen. So let's go inside and check it out. So Corey, Celestron has a really new, exciting, unique telescope. Tell me about the RASA 36.
Yes, the RASA 36, it's a 14-inch RASA. We have had the 11-inch RASA out there for a while now, and we have been secretly developing a RASA 36, a 14-inch version of it. It's still at f2.2, so you will get you very good speed, but with increased aperture.
And this is a really wide field, high-tech camera, astro imaging camera. You could capture incredible wide field views of the Milky Way, big vistas of comets, but there's a really special application that this telescope is perfect for. Talk a little bit about that.
We've been getting feedback from different people. One of them is from a lot of users in the SSA community. SSA stands for Space Situation Awareness. What that means is space junk detecting. More and more satellites are out in orbit, and inevitably they will hit one another, and they become space junk. A lot of them will stay up there for 25 years, and depending on in what orbit they're in, you can be up there forever. What SSA community does is they track these junk so that we can notify the satellite operators so they can maneuver to avoid them. We identify the need, we find a solution. We want to make astronomy fun, and at the same time, we also want to keep everybody safe.
For over a decade, the FirstScope has been one of our customers' favorite products. It's easy to use, affordable, and provides really impressive views for a scope of its size. When the time came to update the FirstScope, I teamed up with renowned lunar imager Robert Reeves to create a telescope that would inspire the next generation of amateur astronomers to explore the moon.
Hello, my name is Robert Reeves. For the past 59 years, the moon has been my passion. Why? Well, the moon is the closest world to Earth. The moon is in our sky almost every night. The moon is close enough that we can see amazing detail on the surface with even modest telescopes.
The Robert Reeves Signature Series FirstScope is more than just a telescope. It's your guide to the moon. The telescope tube is a map of the moon's most notable features, so you can learn the moon's geography. This telescope walks you through the basics and unlocks the entire hobby of astronomy, making it fun, easy, and accessible for everyone.
So I invite you to get out under the stars and enjoy a voyage to the moon.